Please hold. Okay, hi everyone. So the next talk is starting. Please be seated. And the next talk is going to be about a topic that is probably either was or still is very relevant to all of us. The talk is titled Migrating Pinterest from Python 2 to Python 3. So please give it up for Jordan Adler and Joe Gordon.
How's everyone doing today? Good afternoon. All right, that's what I like to hear. Joe and I had a lovely flight coming here with a bit of delay, so if we are groggy and stumble a bit, bear with us. My name is Jordan Adler. I'm a software engineer on the API platform team at Pinterest.
And I am Joe, and I'm an SRE on the same team.
And we're from Pinterest, as I said. Our mission at Pinterest is to bring everyone the inspiration to create a life they love. Who here has heard of Pinterest? Okay, most people. For those who don't know, this is essentially what we aim to do, and for me, a life that I love looks something like that. There are cats available too, so please, no flame wars. We're going to talk a bit about our Python 3 migration project, some of the pitfalls the approach that we took, and some of the pitfalls that we discovered along the way.
So when Pinterest started, it was one giant Django app. I think this is a testament to Django, how well it worked. Since then, we've sort of migrated to a much bigger and more complex system. And now we still use Python as a really essential part of our system today, and it serves every single request for every single over 250 monthly active users. And Python's speed and flexibility is really essential to enabling quick experimentation and iteration for Pinterest.
When we started so our problem statement here is essentially that we needed to migrate this large code base from Python 2 to Python 3. I don't want to go into the motivation for that. I think we're all pretty clear at that at this point, and hopefully that's not something we have to continue to discuss. But as we look forward to moving to, or as we started to think about this problem, it's kind of difficult at our scale. We have a very large code base, 2.6 million lines of codes, excluding dependencies. For context, the Linux kernel, with all its modules, has around 24 million lines of code. CPython only has around 1 million lines of code. So we had a very large code base that's about twice as large as CPython itself. Complicating this further was also the age of the code base. We had over 10 years of many authors focusing on their problems and making incremental changes towards that. And Pinterest is a growing company, and we still have many folks editing our code base every day, and in fact, we have more now than we've ever had before. Additionally, this is a multi-stakeholder effort. We have a shared code base with dozens of teams, different goals and objectives, and we've had cases, we have abstractions that are, for which we've grown beyond the need in our code base, and they haven't necessarily been actively managed. So the coupling situation in our code base is suboptimal for this kind of problem. And when we thought about how to solve it, we considered Pinterest engineering principles. These are our guiding principles, the facets and characteristics that we use to consider our approach to solving problems at Pinterest. And based on these principles, we decided to take an incremental approach, where essentially we incrementally de-risk the migration until we could run code under both 2 and 3.
So the rollout plan was sort of long and complicated. This is a multi-year project, actually. The first step is to make sure Python 3 is available in all our development systems and production systems. The next step is to start to upgrade all our dependencies, all our requirements. We sort of audit everything and sort of upgrade our internal and external dependencies. Then we decided to featureize our code base, and we'll talk about that in a minute. And we want to sort of do a test-driven iterative process here, and so we actually want to make sure as we do this migration, code works under Python 2 and Python 3. And to do that, we're using unit tests. Once all the unit tests work under Python 2 and 3, we switch everything over to Python 3 in production slowly, very, very slowly. And only at that point can we actually start dropping Python 2 support. And then once we drop Python 2 support, then we can actually take advantage of all the really great new Python 3 only features. To upgrade requirements, we sort of want to start at the bottom of the dependency graph. This is because, as I said before, we're actually trying to do it based on test-driven, and we can't actually test a piece of code that has hundreds of dependencies that don't support Python 3 yet. And to do this, we've been using a tool, Can I Use Python 3? Anybody here heard of it? Okay, a few people. So hopefully this is a big takeaway. This works. This uses the the version classifiers under the cheat shop. So essentially, anytime you go to pypi.org, you actually see it says Python 2, Python 3, or something like that, or the license. We actually use those that metadata to tell if something's Python 2 or 3 compatible. As a bit of a side note, we actually had to fork it and add a few features to it. It didn't work for our use cases. 2 is specifically internal dependencies and dependencies where we haven't upgraded it. But the newer versions of the package actually support Python 3. I think the upstream maintainer thought we shouldn't do that in general, and I agree with them, but we were a bit of a funny point and we couldn't change that. Related to that, we have a lot of unmaintained dependencies. Many of these packages were over 8 years old and had to be upgraded slowly. 8 years of changes from some big thing like Flask over a period of a few weeks. And to make sure people don't add new dependencies that are not Python 3 compatible, I've been using can I use Python 3 as a CI test for our requirements file to make sure nobody adds new things that don't support it. And lastly, one of the ways we got around some of these sort of edge cases is we've been using version class environment markers to say only install this code under Python 2 or only install it on Python 3. Only install it under Python 2, maybe it's not 3 compatible yet, or we don't want to deal with that yet, or we're going to sort of delay that work to a different point. Or it's a code that's been backported from Python 3 to Python 2, and there's a few of those as well.
When it came to migrating our own code base, there were 2 approaches that we considered, 2 tools out there in the ecosystem. The first one is Modernize, which is a set of fixers, code transformation tools built around the 6 module, as well as Futurize, which is built along the Future package. And they both take different approaches to solving the same problem, which is writing code that can run under Python 2 and Python 3 equally well. For our use cases, we decided that Futurize was a better fit for us. Future is by the way, for those who aren't familiar, Python Future is a great library. It's out there. It includes a lot of fixers. We'll go into some of that detail later. There's a code sprint. If you're staying for the code sprints, we'll be taking some time to iterate on it and upstream a lot of the things that we discovered at Pinterest, and hopefully iterate on it to the point that we can give it a 1.0 final release. So if you're here next week, please definitely drop by the development sprints and join us to get Future at 1.0. So Future has a set of fixers. They are organized into 2 stages. There's many fixers in each stage. The first ones tend to be low risk and require less effort, manual adjustment after applying the fixer. The second stage includes more nuanced and complicated changes. There's also a number of things that Python Future doesn't cover. For example, the bytes and strings. Teasing out whether something should be a byte or strings is not something you can programmatically do.
And I mentioned before that this uses fixers, and I'm giving actually a talk tomorrow on sort of the details of that. If you're interested in more on how that works, come to my talk tomorrow on syntax trees in Python, automated code transformations.
So by applying, as we futurize our code base, the process that we use essentially to apply each fix individually with linters and continuous integration tools to prevent regression. So if we had a package that's migrated over to Python 3, we require that it continue to run as expected under Python 3 with our unit tests. By applying each fix individually, we simplify the cognitive overhead of the change by logically grouping by each fix. This makes code review faster. It also enables us to deploy incrementally, which reduces the entropy per push, which is nice because essentially some of the risk here is discovering issues as we deploy. There are also the fixers aren't style aware, and we don't have any automated enforcement of style for things like black. So after running the fixer, some manual effort was required to ensure that some of the fixers passed under Flake 8. And unfortunately, part of the process is also discovering what your unit test code coverage looks like. Ours was relatively good, thankfully, and if that's not the case for you, I would strongly recommend that as the first step before proceeding with any major refactoring, certainly one of this scale.
One of the challenges we face is, so where do we start with this whole thing? So we could start with some external dependencies, but we actually wanted to start working on the code itself. We can actually futurize large parts of the code, but we actually want to now see what code actually passes into Python 3 itself. And so to do that, we had to introspect sort of the internal dependency graph. So our graph is actually really complex and confusing. With 2 million lines of code and not ideal abstractions, you get this sort of spaghetti ball of chaos and confusion. And so we couldn't actually just say, hey, start with this module. This module has no dependencies besides third-party dependencies. So we actually had to introspect that. And to do that, we did something that is generally weird to do, I think, which is monkey patching import. It worked pretty well, surprisingly. And so the way we did this is we actually built a list of modules that run under Python 3. So we take the tests we know that work under Python 3. We see what they import. We get the dependency graph from that. Then we apply the same tool, the same monkey patching of import, onto all the tests under Python 2. And then we see which tests have what dependencies. And we take that and we find the Python 2 only tests that have the fewest dependencies that are not ported to Python 3. And then we started with those. This was a really great way for us to sort of solve this sort of bootstrapping problem and allow us to iteratively build up and start at the bottom and work our way up. The next step is we actually want to run our tests under Python 2 and Python 3. Most people's test runners hopefully are very clean and simple. Ours was not that. Ours was actually pretty terrible in sort of every way. Our test runner actually imports most of the code into the repo. So what that means is that we actually, to get the test runner to work under Python 3, you have to do most of the work to get the whole repo to be Python 3 compatible and to work under Python 3. And so to sort of solve that problem, we actually pulled out a smaller test runner that didn't import the whole world effectively, and a smaller test-based case that sort of solved that.
Yeah, and I think one of the things to note here is that the fail paths can change depending on the fixer. As I said before, some things are observable only at runtime when you actually run the thing in production. But there are the different classes of errors that have different classes of potential errors that have different classes of fail paths. So syntax errors generally are detectable by Flake 8. Flake 8 also, some of the scoping changes are detectable by Flake 8, and there's a handful of other things that can be easily picked up. Some things are detectable at import time. So for example, any bad dependencies or code that's evaluated on import, statements at the top level of the module. When you import that code into your production code, or sorry, into your test code as you run the unit test, it will fail upon import at the import stage, which is great because you don't actually need to have unit tests for the exercise path. You just need to actually make sure it compiles. And then there's another class of errors which are only detectable at runtime, either via unit tests that exercise those code paths and enable you to discover the failures, or unfortunately, if there's not good unit test code coverage, you're going to have to detect some of these in production as you release these changes. And so with that in mind, so complicating that further, and so that's one set of characteristics that makes some of these fixes more complicated than others. Another is that we just have a large and complex code base, right? If you spot test a code transformation on a portion of our code base, given its large and complex size, it could potentially have effects on another part of the code base that, quite frankly, you didn't even know existed. It's not possible to have 2.6 million of lines of code in your head, especially when they change this rapidly. And so some amount of stochastic thinking is required to really understand how to do a code migration at this scale. Test coverage is part of the challenge here, too. If a particular change to a particular portion of the code base does not have test covering for that path or that particular branch, or even, quite frankly, if the test that's being done is of low quality, if it doesn't check that the actual responses are as expected and it doesn't have good, even if you have good coverage, it doesn't mean your coverage is high quality coverage. And so that can be a challenge as well. Additionally, some of the fixers simply cannot, there's limitations in the fixers themselves. For example, old div safe and fixed dict, these use approaches that were a little more conservative. The fixers are more conservative, which is perfectly reasonable and exactly what you want to do, but not necessarily what we want to commit into our code base. And so those required some manual adjustments after having run the fixer. And there are some things for which there is no fixer. For example, the string and bytes difference is something that you kind of have to go variable by variable and decide what the correct approach is there.
So the good, a lot of things actually worked really well. I think the rest of the talk is going to be about terrible things, bad and ugly. But I want to stress that a lot of things actually worked really well. In fact, most of the hard work has been done for us. It's a bit of a side note. Python 3 is actually 10 years old. I think it's 11 years old now. So we're actually not talking about migrating to a new thing. We're talking about migrating to an old thing. As a bit of reference, our code base is roughly the same age as Python 3, which is, I think, interesting side note. So often the only changes required for a lot of these changes was actually making sure we passed Flake 8. Everything else is sort of done for us. So I think the really good things here are Futurize worked really, really well, as did lib 2 to 3. So a few examples. Here's one, print with import. Hopefully everybody here knows about this Python 3 change. Anybody be surprised by this one? OK, nobody raised their hand. That's good. Right, in Python 3, we have print, you have to pass in parentheses to it. And so if you have, on one side here, we have the Python 2 style, and we have the result of the fixer. and it sort of handles all the cases perfectly, right? You have bare print, you have print with high, you have Python 2 style, and Python 3 style print. That all works. You have rerouting to standard error. Everything works great. Another one that worked really well is except. Python 2 has this really tricky notation that actually has caused multiple problems in the past for us. If you want to do except exception, comma e is the variable for the exception, that you caught all exceptions here. But the other thing you may want to do in this case, if you want to catch several exceptions, the notation you're supposed to use is except parentheses exception 1, exception 2, close parentheses, comma e. But a lot of people just do except exception 1, comma exception 2, in which case you catch an exception and you store it in the value for exception 2, and then you cause all kinds of weird problems because you essentially are monkey patching something at runtime, and it gets really confusing. So Python 3 decided to say, no, we don't want to do that. And it turns out the fixer works great for that. It also works in this less clear notation here, except exception bracket A. And you can see here on the other side in the result here, it actually takes the arguments passed into the exception. So in this case, it would actually be B. A would be B in this case. But this is sort of one of the limitations of fixers here. It doesn't know what variable to use, so it has a nice simple variable xxx to do change me. And so presumably you should be changing that and not sprinkling it all over your code base. Another one here is meta class. Under Python 2 and Python 3, the meta class notation changed significantly. Python 2, you do double underscore meta class equals meta. But in Python 3, you do class foo meta class equals meta. The problem with that is you can't have a code base that supports both of them. And so this is a good example where Python future has a shim that you use. You do from future utils import with meta class. And in this case, the fixer does it all for you right away. Another one is absolute imports. So under Python 2, there's this concept of doing implicit relative imports. So you can see here we have import foo. Foo is a module in this directory I'm in. And I'm accessing this variable, this constant x. The confusing thing about this is that it could be, if foo happened to be named OS, let's say, then you could actually it'd be unclear what you should import. Are you importing the OS in the directory or importing the standard library OS? And this has caused multiple problems for us over the years as we refactor code, and the implicit import caused all kinds of problems. So Python 3 has absolute imports, so you have to do explicit relative imports. And once again, the fixer does it in most cases, but there are ambiguous cases in your code base. And in that case, sometimes feature will break, and you'll have to fix a few of them by hand, but it fixed 90% of the issues right away.
Others were surprising. A large code base means we have lots of edge cases. Here are some of the issues that we hit along the way. So this is a nice simple example here. We have 1 divided by 2. Under Python 2, we get 0, right? This is because it's an integer. Anybody know what it should be in Python 3? Just shout out the answer. That's right. OK, so this is a nice simple one. In this case, Python 3 makes sort of behavior sort of more expected. I know many of you say, but it's not. These are 2 integers, and that's not how division works. But this is how I think humans think of division, and so it's a nice change to reflect how people really think about it. Here's another interesting one. We have rounding, round 9, comma 1. Under Python 2, we get a float, 9.0. Everybody guess we get in Python 3? We get 9, not a float. So we get an integer now. Once again, I think this makes more sense. It sort of reflects what we put in, we get out. Here's an interesting one we have. This is one I thought was really fascinating myself. We get round 2.5 under Python 2. We get 2, right? We round to a number. What do we get under Python 3? 3. Anybody know why? That's right, banker's rounding. Very impressive. So the idea here, previously you would round down to 0 every time. And the problem with that is if you're a banker, let's say, and you have a bunch of numbers, the error from rounding adds up over time. But if you round to the closest odd, it'll hopefully balance out over time because you're assuming your numbers are not distributed, they're randomly distributed with regard to where they are in the float. And so once again, this actually makes the numbers sort of work better in a better way, although technically these are both completely valid answers. Rounding 2.5 has 2 correct answers, not 1, and so this is sort of a weird case here. Here's another one. You have x equals none. Maybe it's a fallback from a function that it returns a value, but in some cases it returns none. And we're trying to compare x to some constant, in this case 1. Under Python 2, we get false, right? None is not greater than false. Python 3, any guesses? Yep, we get a type error here. It turns out you can't compare none and int. That doesn't make any sense. I don't know how we could have done it before. This is a case where we found in our code base that lots of people sort of assumed this behavior worked, and we have lots of edge cases that hit this. Here's another one we have. Month equals 0, 1, right? It's January. We're going to try to print the month. Python 2, we get 1. Makes sense? Python 3, anybody?
Nobody? Okay. We actually get invalid token. It turns out this notation is not correct. The reason is because under Python 2, 0, 1 is not base 10. That is base 8. It is octal. The 0 is for octal here. And so you can't actually do, for example, 0, 9. And in Python 3, they say, hey, that's not a great idea. This is super confusing. It turns out it is super confusing in our code base. And so the actual correct notation is 0, 0, 1. And that'll work in both cases. But in most cases, you could actually just drop the 0 and then make it just be 1 and then don't use octal, because using octal in most code bases is a bit unusual. All these changes are sort of making the numbers align more consistently with people sort of expect them to do. The rounding, the comparisons, everything else. And these are all part of a big PEP 3141. And it was a numeric tower. And it sort of simplified the whole process and made it much more aligned with reality. This is one of, I think, the big surprises for us in this migration was how many edge cases there were here that we actually hit.
So we also hit a number of issues you can imagine around bytes and string. So here we have some example code. We get a user ID integer from some part of our code base. We cast it to a string under Python 2 by passing it to bytes. Any guesses what happens in Python 2? It's a string. What about Python 3? Yeah. Essentially, we get a memory error, because in Python 3, when you pass a value to bytes, it assumes that that's the number of bytes that you wish to allocate. So you can imagine our very large user IDs resulted in us allocating more bytes than we had available in memory. Not fun. We have this case here where we iterate over a byte string. Any ideas what this might produce under Python 2? So it'll produce 1, 2, 3. What about Python 3? The ASCII code points. Yeah. So essentially, in Python 2, this byte, the byte string is treated as a byte sequence. And so under Python 2, it's treated as a character sequence. And so each thing is interpreted essentially as a character that was passed into the byte literal. And under Python 3, no encoding is applied to it, and so the byte string literal is interpreted as the ASCII code points that correspond to those characters. Here's another example. So we have string.letters and string.ASCII letters. We use those in our code base. Under Python 2, they return the same thing. In reality, string.letters is locale specific. Under Python 3, it's gone. And so part of the reason that it's going is because it is locale specific, and it was dropped as part of going Unicode native. The locale specificity made it kind of difficult to debug, and so this is generally, I think, a good change, as most of these are. Here's another example. We have a bit of Unicode code in our code base. We pass in our encoding UTF-8 signal, a hint to the compiler. We create a new exception with some value that we get passed in from elsewhere in the code with some emoji characters in it, perhaps user inputted text. In Python 2, this is not allowed. Essentially, the exception expects an ASCII encoded character. In Python 3, this works just fine. And so the root cause of much of this is essentially reorganizing the containers, the sequence containers, or the sequences for Unicodes for strings and bytes. So in Python 2, string and Unicode are sequence types along with list and tuple, and there's a couple others. The decision of which one you use as a programmer was decided whether you wanted an 8-bit interpretation or a Unicode interpretation, right? So typically, the 8-bit was ASCII by default. In Python 3, this distinction was removed. A new type, bytes, was introduced for representing raw binary sequences with no application of any code map. And then the string type was intended to present an encoded overview of a bytes, or an encoded representation of a sequence of bytes.
So let's talk about scoping here. This is what I think a lot of you have probably seen. Under Python 2, we have a list comprehension. Anybody guess what should be in Python 2? 9. Anybody actually use this kind of code in their code base? I'm curious. A few people? OK, we use it a lot too, surprisingly. Under Python 3, I think this is sort of a weird thing. There's no scope here. You leak variables. Python 3 fixes that. It says I is not defined. That makes a lot of sense here. Although it is a nice behavior you could use before, so you have to refactor some code. This is actually a good example where this is really easy to spot with actually Flake 8 will spot this. but it's not always easy to refactor the code programmatically, so you have to get in and actually manually modify the code. Here's a bit more complicated one. We have another interesting sort of scope on our list comprehensions. Anybody guess what this should be under Python 2? It's a little confusing code. We have a variable A and B, and it turns out B should actually be 2, right? We're just going over B is using A. Python 3, any guesses? No, it gives you an error, a name error. It turns out A is not actually defined here. So it turns out, this is a quote from a bug I found. I'm not sure who the author was, but if you're in the room, thank you very much for writing this. This is because list comprehensions are now implemented with their own function object, like generator expressions always have. Effectively, what this is saying is this code should have never worked. Under Python 3, they fixed that, and it doesn't work. Under Python 2, it does work. As a bit of a side note, if you do this outside of a class as a top level, it does work. So this is sort of a weird edge case I think we saw once, and we're just sort of blown away by it, and then it turns out it never should have been there. Here's another one for scope. Anybody guess what this does on Python 3? Print out the locals inside of a class. Any guesses? We get one local here. In this case, it is self. Under Python 3, we actually get 2, which is now we have class. It turns out you hit this if you do anything in your code with locals, and you're iterating over locals and expecting certain values to be there in locals and certain ones not to. And this is actually a fairly easy one to fix in most cases, but it required manual changes every time. Here's another one about dictionaries. Dictionaries is a big thing to change under Python 2 and Python 3. Here we have a function foo. We're passing in b equals 1 and a equals 2. And we're printing out the keyword arguments. Under Python 2, we get a equals 2 and b equals 1. They're actually switched around here. Under Python 3, any guesses? It's actually a trick question, as you'd imagine by now. It actually depends on when you run it and what version of Python you're running. So if you run it under Python 3 to 3.5, the ordering depends on when you run it. If you run it twice in the same code base, it'll always be the same. But if you run it twice in the same instance of Python, it'd be the same. But in different instances of Python, it'll be different. And then under Python 3.6 and above, it actually changes to the ordering. It's always b equal b1, a2. And this is because there's two major changes to dictionaries under Python 3. The first one is hash randomization was added. It's intended to protect against denial of service attacks with big O of n squared complexity. And this was true for Python's 3, I think, through 3.5. And this is true beyond. There's randomization in there. And so that's why we get random ordering when you run at different times. We are using Python 3.5 in a few instances. So we decided to hard code a random seed for our test environments. I think we picked some number so it's the same every time. And this actually made it much easier for us to test and sort of isolate these problems and deal with them later. And part of the problem we're not dealing with them now is because there's another part, which is under Python 3.6 and above, there is a new dictionary that is more compact. It's, I think, 20 to 30% more compact. It was done, the main motivation for it is to use less memory, but one of the interesting side effects is now order preserving. But as you see here in the release notes, the order preserving aspect of this new implementation is considered an implementation detail and should not be relied upon. It turns out that under Python 2, we had a deterministic order. In Python 3.6, we have deterministic order. And a lot of people made assumptions about the ordering of dictionaries under Python 2. And so not relying on this has been really hard for us, especially when you have hundreds of developers working on code independently. Sort of a common case of this is maybe you're printing out a string in an exception, or a dictionary in an exception, and you're sort of assuming the ordering of the representation of it is always the same. Another case of Python 3, here we have a dictionary. We're printing out the keys. Python 2, we get 1, 2, 3, as expected. Anybody guesses Python 3? We get an error. We get a type error here. Actually, it's dict, keys, and list. It turns out there's a huge change from Python 2 to Python 3 on dictionaries. Now we return dictionary views for keys, values, and items. And iter items, iter, et cetera, are all gone. And one of the things is this is more of a set-like a component set of a list-like thing. And in this case, you cannot add them together. You can also not pass it into sort because you can't sort this thing that's only an iterable and not actually a list. In this case, this is actually a fairly easy one to fix, and there's some good fixers for it under Python, under Futurize.
There are also some changes around exceptions. So here we have a bit of code that raised an exception and then takes the sys.exe info to get information about the caller. Any ideas what this might produce under Python 2? think we scared you guys. As you might expect, it returns 2 exceptions. What about Python 3? Yeah, so it returns 1 exception and then none. Any idea why that might be? Yeah, that's right. So essentially, the thing that changed was the definition of the phrase handling an exception. Under Python 2, handling an exception is defined as executing or having executed an except clause. Whereas in Python 3, it's defined as executing an except clause. So the distinction here is that you can no longer expect sys.exe info to be available outside of the context of the except clause. And much of our code base depended on this behavior, and it's difficult to discover. Here's another exception issue. From exceptions, import key error. Any idea what this might do in Python 2? Nothing. It does literally nothing, not just because it's not doing anything, but also because the from exceptions import foo process is a no-op. In Python 2, the exceptions were pulled into the built-in namespace, and so this line was basically ignored. What about Python 3? In Python 3, the deprecated exceptions module was removed. And so essentially, this is a vestigial holdover from Python 1, where the exceptions were in the exceptions package. In Python 2, it was deprecated, and so it's available in the built-in namespace. In Python 3, it was removed. And so this no-op became an error in a way that we would not have predicted. Some things were painful.
So this is a really interesting one for us. This is actually something that's, I think, near and dear to a few of my colleagues right now. Hashability. We have this class here, myString, and myString defines EQ for equality. In this case, it's not doing anything special. And we try to print out the hash of myString PyCon. Anybody guess what that'll be? A big number, right? Positive or negative number. It's a really big number. Python 3. Any guesses? Type error. That's correct. Yeah. So it's unhashable type. Specifically in Python, you should always have if 2 objects are equal, then their hashes should be equal. And that should always be true. And if you define your own equality operator, you are probably you're probably breaking that explicit contract that should always be done. Under Python 2, it lets you sort of shoot yourself in the foot and have a happy day. Python 3, they actually said, no, this isn't a good default behavior, and they actually fixed it. So if you define EQ, you have to define hash as well. And this turns out to be a fairly easy thing to fix, but it's also very subtle and very confusing. And the edge cases under Python 2 actually, I think, are the sort of the scarier part, that this could cause all kinds of weird problems.
So one interesting case here is we had a string that was coming in from a user-generated content that contained ASCII and Unicode, or not ASCII and Unicode, but it contained essentially Unicode characters, including emojis. So we were iterating over each character in that sequence and printing out some information about that character. Here we've converted to ORD and hex so we can look at the code points. What do you might expect this to look like under Python 2? Well, your first character is going to be your code point for the ASCII letter A. The second character, 20, is the code point for space in ASCII. And the next 2 characters are the code points that represent bytes that combined refer to the lovely emoji that we have here. Any idea what this might look like under Python 3? How many prints do you expect to see? 3. Right. So in Python 3, we logically group the Unicode characters, and we treat them logically as characters, which is correct. This is no longer exposed to the Python developer. Essentially, this is an implementation detail under the surface because we're encoding in the Unicode character sets. However, when we were debugging this, we had some inconsistencies because in some of our environments, we were seeing the Python 3 behavior under Python 2 as well. Any idea where that might be? Not quite. So in Python, below a certain version, you could compile what's called a wide or narrow build. And essentially, that would change the internal representation for characters to be UCS2 or 4. The gist of it is that it would either use 2 bytes per Unicode character or 4 bytes. If you have 2 bytes, then what happens is, or so-called narrow build, then multi-byte characters are characters that refer to a code point that cannot be encapsulated in those that number of bytes, you get essentially two separate characters that combined refer to the actual glyph that you care about. In Python 2, you can also do a wide build, which is what we had in some of our environments. And so the challenge here is that the compile time flags that we were using to override the behavior here was not consistent in all of our environments, which was something we did not think to have to expect.
So here's another really fun one. We have from cstring import string IO, and we have two things. We have some image data as bytes and some text as Unicode. Anybody guess what happens to Python 2? It just sort of works, right? Nothing actually happens. We actually get no result. We're not printing anything out. Under Python 3, any guesses what we get? We get an error here, actually. We get module not found error. Turns out cstring IO is deprecated and removed in favor of IO, bytes IO, and string IO, and those are in Python 2, actually, as well. So let's try this code again. From IO, import string IO. We have string IO, the bytes, and the Unicode. Under Python 2, we actually get a type error. It turns out for string IO, it requires Unicode, and bytes IO requires bytes. And actually, thankfully, in Python 3, we get the same behavior. But here the catch is we've been using the from cstring IO, import string IO to handle both cases. Now we actually have to go through and manually sort out each case. And there's some particularly ugly complications around this. Under Python 2, opening a file by default opens it in binary. Under Python 3, it opens as Unicode. The CSV module changed some behaviors in a similar way as well. So you combine all these three things together, you get this really sort of hairy knot of these weird binary Unicode problems to handle.
One of the fun things about a migration of this size and a code base of this size is that your Python code does not run in isolation. It integrates with other components and other systems that are not necessarily built with the same technology stack. In this case, we have some Node.js services or some JavaScript environments that communicate with our Python stack. And so we're going to drift quickly over into the JavaScript world. And we're going to run these two statements in the Node.js REPL. What do you expect might return from this based on your understanding of computer science in general? Yeah, so essentially in JavaScript, numbers are always 64-bit floating points. Because both of these numbers are outside the threshold of precision for doubles, you get capped at the functional equivalent of max int or max double. This is defined in IEEE 754, which if you're curious to learn more about, David Wolver will talk about it tomorrow in a lovely talk entitled IEEE 704.000. So the fun thing about how IEEE 74 numbers are implemented is they're not necessarily accurate. They're accurate enough. They're sort of like scientific notation. So to work around this in our code base, what we did was we converted longs to strings when passing to JavaScript. Unfortunately, our isInstance test for longs doesn't work under Python 3 because in Python 3, as well as 2.6 to some extent, ints and longs are effectively the same type, right? And so our test to see if it's a long did not pass, and so it was not coerced into a string, and it was passed to the JavaScript system directly as a numeral, or a numeric literal, which it was not able to interpret. That means it no longer works as Python 3. We had to go back to the drawing board to figure out how to solve that problem.
Another challenge we dealt with is mocks. A lot of the fixtures we use actually do a lot of things great for us, but I don't think any of them actually handle changing mocks. So here we actually have a mock. We're mocking built-in open in Python 2 with open, not a file here. As a hint, this is not actually a file, so if you weren't mocking it, it will throw an exception, but in this case, nothing actually should happen because we're mocking open, and open will just do nothing, and it'll be fine. It'll be a magic mock, and we get nothing under Python 2. Any guess we get under Python 3? So let's actually see. It turns out module not found. It turns out built-in was renamed to double_built-ins was renamed to built-ins. And that means actually the mock is no longer valid. So we're actually not mocking the thing, but we're trying to mock a thing that doesn't exist until we actually get mock throwing the exception. It turns out we have lots of code now where it says, if Python 2 mock this, if Python 3 mock that. This is something we sort of had to manually find in each case. It turns out these are fairly easy to find. This is true for essentially all the standard library changes that are made under Python, including things like built-in.
So these are some of the most interesting edge cases we discovered along the way. We're still in this process, and if you're curious to learn more about some of the things we expect or we will discover as we continue, we expect to update the Pinterest engineering blog with information about the Python 3 migration project as we come closer to a close on that. Hopefully we'll have some information about the impact of that, which we expect to be significant. Thanks for coming to the talk. Since we're kind of short on time here and we're the only thing between you and lunch, we'll take questions at the Pinterest booth on the expo floor at 4 o'clock. Cool. Thank you so much.
Yeah.